everybody. My name is Josh Kalin. I'm here to provide you a presentation on a modified Drake equation for assessing adversarial risk to machine learning models. You can see I've got some co-authors, Dr. David Noever, Matthew Ciolino, and Dr. Gerry Dozier. And I'm presenting this as part of my PhD research, kind of focused around how do you quantify adversarial risk and defend machine learning models in kind of an uncertain world where adversarial attacks seem to be with every model that you produce. And this is kind of the goal of this particular work, is to provide some form of framework around how do you probabilistically estimate that adversarial risk, and then how do you come about finding ways to reduce that adversarial risk for production pipelines. So you can see on the left-hand side, we've got some bios from myself, my co-authors, and then I gave you just a little sneak preview of the briefing structure for what we're doing here. What is adversarial risk? Some examples of successes and failures in kind of assessing these predictive models, actually using this modified Drake equation for assessing risk. We did some examples, so BERT, GPT-3, really common models in the field right now, state of the art, and kind of understanding what their risk profile might look under our probabilistic framework. Then just evaluating like a set of models. So if you had a tabular form that put yourself against some of the models that are out there and you have your new model you just produced, how do you rack and stack against other models that might be in your environment? We also looked at the correlation between related variables. So our construct is kind of interesting because those variables are or do have some interrelationship in them. And then just kind of going over the conclusions that we got throughout this paper. So what is adversarial risk and why do you care? So adversarial machine learning is kind of this emerging major field aimed at the protection of automated machine learning systems from security threats. So you produce a machine learning model, you deploy it to production, and everybody likes to just take the keys off and just say, hey, we're moving along and we're going. Unfortunately, adversarial attacks are very common these days, especially for very popular frameworks. We like to affectionately call it download and deploy. You went and found a network online, you put it in your production pipeline, you started serving up your customers some results. Unfortunately, a lot of those frameworks, because of the nature of the architecture of the paper and that the weights are freely available, it becomes a risk. There's a risk factor to the fact that you've now supplied everybody the keys to exactly how you build, deploy, and analyze your model. So what do you do to quantify those risks and establish a framework for improving models incrementally? So in a lot of business frameworks, they talk about KPIs, like key performance indicators. For machine learning models, that can be very difficult to quantify how is a machine learning model doing better? How do we know we're getting better in this environment? So our goal was to explore the practical factors needed to consider before fielding a new machine learning model by modifying this probabilistic framework. So just some brief examples of successes and failures in assessing predictive models. And, this is just kind of just a brief survey of different methods, and I'll just touch on each one of these very briefly, but within our paper, there's the sources for all of these particular methods, and you can kind of see what some of the other authors were looking at. But diversifying or augmenting training data, this is one methodology that says your data set is the vast majority of the derived weights. In other words, your machine learning model that was built learned from that data and it learned the distribution. And so some of your adversarial risk does come from the data. So how do you get rid of that? Well, you diversify or augment your data. You add some new data, or you do what's called image or text augmentation. So you change the data but maintain the same context. Ensembling or model voting. This is a very successful methodology, but it's really heavy. So when you ensemble models, you're essentially saying, I'm taking two or more models and I have them vote and give a response back for the query. Unfortunately, as you increase more and more models in a system, typically you're going to either increase the computational power required or the speed. So you're going to reduce speed. That's not everybody's cup of tea because you're just basically increasing the infrastructure cost to deploying these models. Obfuscation. So when you deploy a machine learning model, maybe you don't make it open source, maybe you don't provide the model weights, and maybe you don't even release publicly what the back end is for those particular models. We wrote a separate paper a number of months ago, but where we actually probed machine learning models and were able to derive both their data set and the underlying architecture for that particular problem through some structured probes in the image and text space. So I don't think obfuscation, even with the best intentions, may not work in some cases, but it can. And that this is one of the more successful papers. Active learning. So it's this methodology that says, one of the original use cases of active learning in the machine learning field was to say, if I have a set of 1 million images, what does it take for me to get to 80% accuracy on a model? And so what you would do is you'd incrementally provide images to the model, and you'd see what kind of accuracy you get back. Because you have labeled data, because you know all the right answers, you can actually evaluate kind of the knee in the curve. How do you find out the accuracy and the availability of those particular models? In the active learning sense, they were trying to teach the model how to avoid adversarial attacks. Finally, protecting the model descriptions or firewalling, like we talked about before. This is kind of what we were doing, was saying how many probes would it take to find an architecture or data set. I feel like, yes, at the nation state level where, you can protect models at these, super high levels and do those kinds of things, sure. Maybe that's available to some folks, but the vast majority of places, even big tech, are not going to go to such great levels to protect these models. And so the best thing you can do is reduce your adversarial risk in the face of an ever increasing attacker-focused world, I guess you would call it. So, and all these strategies should appear in one or more of the proposed terms for this equation. That was kind of a goal of ours. We know these papers exist, we know these problems exist, so how do we capture that in some framework? So I love this picture here. I love this way they present this for the Drake equation. So if you haven't heard the Drake equation, Frank Drake proposed an estimate to the potential number of intelligent alien civilizations in our galaxy. And he has all these great factors here that kind of go into that. I'll just touch on each one of them because we're going to go back over them in our modification. And so I think it's kind of important to think about how they correlate to each other, right? So R, the average rate of star formation every year in the galaxy. F sub P is the fraction of those stars that have planets. N sub B is the average number of planets that can support life and stars that have planets. The fraction of planets that actually develop life, the fraction of planets with life that actually go on to develop intelligent life, the fraction of intelligent life that release detectable signs of their existence, the expected lifetime of such a civilization for the period that it can communicate. And finally, you're looking at the number of civilizations in our galaxy with the communication, where communication might be possible. So I think the important thing to look at here is that some of this is not really, you're not able to go and say, I know for a fact that the fraction of planets that actually can develop life is blah. We can observe, we know what we can observe, we know what our estimates tell us, and we know what constitutes an inhabitable planet. And I kind of believe in that framework for how we want to assess adversarial risk in machine learning models. I can't tell you for sure how many attacks you may see in a year. I can't tell you for sure that folks are going to use these types of attacks because you released your model weights. And honestly, nobody may ever attack you. It's always that big fish, little fish. You may just deploy a machine learning model to your website and nobody cares. But I think it's one of those places where, as businesses increase the usage of these particular models and techniques, we also need to focus on how do we protect them. And this provides a way to show that you're driving adversarial risk down. So finally, my graphic is not nearly as pretty because I am not that talented with creating infographics, but I'm just going to go over with y'all the adversarial risk using a modified Drake equation. So we kind of quantify this as the number of successful adversarial attacks, and we'll kind of show you some of the ways that we've adjusted that as we went forward, because depending on how you looked at this, you could have a lot of adversarial attacks, and obviously that's very possible because there's very many permutations. So we made it relative to the other models so that the numbers made a little more sense. But you can see here that we have kind of this set of parameters that describe machine learning models. The average enterprise size, so are you a Google or are you a 3-person team in a startup? The fraction of models published, so are there a bunch of models published in this paper, in these spaces or not? The number of parameters, so if you look at like GPT-2, GPT-3, you know, one of the smallest GPT-2 formats right now is 124 million parameters. I mean, that's just insane in some ways to consider. You know, you're not going to go look at the connections that occur, for instance, in a neural network or a transformer. You're not going to analyze each one of them to derive the exact path that a query took through your model. You could do that, but computationally, it's just not tractable. You can't expect every evaluation of that model to include that step. And so the number of parameters is part of our adversarial risk. Your learning ratio, so how aggressive are you when you actually train your models? How aggressive are you in, are you losing information? Are you keeping information? Are you learning too much of the distribution and too reliant on your data set? Input quality checks. So I'm sure if you're familiar with the data sets that are used currently for training machine learning models, you've heard about the fact that there is an error rate associated typically with all these open source models. And Google wrote a paper a while back that I think it was like something like 8% to 10% error in your training data set's actually better for you because you don't overfit the distribution. It's kind of like us when we make mistakes, it helps us learn better. And I think it, you know, I kind of think of that's how some of these neural nets learn. You don't always want the answers to be right because it helps you generalize better in that training step. So completed queries, you know, how many completed queries are you getting through the model? If you're only having 5 people touch the model a day, the likelihood that somebody's going to come out of the woodworks to attack you to get at that model is much lower than if you're pushing through, you know, millions or billions of people through that particular attack. And then finally, attacker query time. So, you know, you got to be concerned with the fact that, you know, do you allow somebody to just hit your model over and over again, or do you let them hit it periodically? Do you time folks out? That kind of stuff. So we're just going to walk through each of these parameters just a little more detail. You know, the original factor here was star formation. So we want to generalize this to the aggregate overall enterprise size. It makes you think about the fact that like Microsoft Windows, you know, almost everybody uses it, and then you have Apple and then you have Linux. But honestly, you know, there's still a large portion of folks that use Windows, right? So that's just a huge adversarial risk there, right? People are going to attack in the cyber domain because they know that there's a large chunk of folks that use it. They don't secure that particular operating system. They don't install their updates. You can think about it kind of like in this respect, you know, how many folks are going to go and do training augmentations or change their model before they deploy it? You know, not a lot. They're probably just going to download, deploy, and get some answers out for their customers. So depending on that enterprise size, that might not be a great idea. So, you know, fraction published, named, open sourced, or fielded in the wild. So how often are you providing out the exact weights, the exact inference code, how you built the model? Do you provide the training data? One of the best ways to kind of describe this in the transformer world was GPT was released, and then GPT-2 was released, and they released the model weights, and they released the inference code, and they released the training data. But now GPT-3 in the transformer world is through an API. You don't actually get the weights, and you don't get the training code. There's some efforts right now on trying to recreate those models open source, because OpenAI has not provided the backends for those particular models. And it's probably because of some of these reasons. They don't want folks going in there and just purposely breaking the model. So, the original Drake equation, this factor considered number of planets capable of supporting life. We're looking at the average number of engineered parameters. So when you fine tune a model and you go learn some parameters, how much risk is there in those parameters that you learned? Did you learn something that actually opened you up to more risk? And I like to think about it in terms of, they have these talks on machine learning and fairness in the models. And what you see is they talk about the fact that there's all kinds of terrible associations that model makes with different ethnicities or different genders or different age groups, because the data they have within the distribution of the data they were trained on only shows certain ethnicities doing certain sports or certain genders doing certain things. Well, you're opening yourself up to the fact that, let's consider it the opposite way. Well, we've learned that this one class is associated with this action. And if an attacker understands how to manipulate that action, they can get that class back out. So if you had a model that assessed your credit risk, for instance, and you wanted to buy a car and you knew how to adjust your numbers just right, you could go buy a car even though you're not at all qualified, because those models don't understand what those numbers mean. They only understand what they've been taught by the data they've seen. The fraction of the learning ratio, so how aggressive you are in terms of learning. This was how often do planets spawn life, and we kind of thought of this as how spontaneously do you learn new information or not. The fraction of input supervisory guidance, so the rise of intelligent life for more primitive forms of the Drake equation. In our machine learning context, this is more about how much did you check the model? Do you have any unit tests or integration tests that make sure that you're actually getting the information out you expect? And are you checking for, I think about a unit test in software engineering where you check for divide by zeros. That's not going to work in the vast majority of packages, or it's going to throw an error warning. It's kind of the same way here. You wouldn't expect somebody to have negative bounds and then go ask to buy a car. So actually checking against those particular ways. And then, and we kind of addressed a few different interesting ways that folks have tried to evaluate these models and to evaluate them against attacks and kind of benchmark that. And there's very simple attacks and there's very complex attacks. And so how do you actually build models in such a way that they're at least robust to some of them? So again, just kind of walking through the last bit here, the fraction of completed queries that return detectable or logged answers. So we were able to detect, essentially architecture data from just some strategic probes. So how often you're protecting yourself from that particular problem, because you will see that folks will engineer queries in order to understand your model's vulnerabilities. The length of time that attackers can query without consequences or timeouts. I think this is kind of the easiest way that you can save your model in the near term. Don't give somebody the ability to query your model 1,000 times in a minute, right? I always think about when they talk about breaking passwords on like a machine, right? And they said it takes 10 seconds to break the password on a machine. And I always laugh because written in the fine print somewhere is that they had to try, 7 billion answers. And one of those answers is correct. So they did break your password technically, but what system that's locked down is going to let you try 7 billion answers in any reasonable amount of time? And obviously there's exploits and ways that you can get around some of that, but just locking down your API, your access to that particular model will go a long way in protecting you from all kinds of issues. So there's an axiom that we derived here because of the research we've done in the past. And it's the fact that architecture and data set metrics are related. Just because you have a unique architecture doesn't mean that the model that's built is actually that much different than a different architecture. Because if the data sets are the same, the models are probably going to learn very similar distributions for a target problem. Look at similar features in those images typically in order to get at high accuracy in those particular spaces. And they're starting to grow away from that. You'll see there's vision-based transformers now, where you're thinking about an image as kind of a language model, and they're building detectors and all kinds of things there. And I think that's going to kind of bring a new age. We're not always focused on convolutional neural nets. But in the interim and in the near term, I still do think they are highly correlated in this way. The first fraction is defining the key parameters related to architecture, and we're computing their contribution to the adversarial risk. And this is important. So I want to just focus on the fact that sometimes your architecture is going to create more problems for your data set, or your data set is going to provide more problems than your architecture. A lot of SOTA or state-of-the-art models today are very complex. They offer great performance. The issue with that, don't have anyone check the answers. If you're just downloading and putting into your system, then you'll open yourself up to risk. And if you just download a data straight off the internet and your own data for fine tuning, you still open yourself up to that very same risk. So now that we've just beaten y'all down with all of these parameters and adjusting this algorithm, I wanted to just take a quick minute to just walk through some example applications and what this might look like. So different ways, right? So we talked about enterprise size. Google has 135,000 employees, and so we use that initially, and you just get this, with 110 million parameters. But just to be frank, if you think about 110 million parameters and you think about 135,000 employees, not every employee is contributing to that particular. Not every parameter is going to open you up to a risk, right? It's a combination of probably tens of thousands or hundreds of thousands of parameters that are driving risk in that particular model. And so we did two things to adjust this down, kind of to the enterprise size, the number of authors in that paper. And you'll see that typically there's a lot more authors on the papers that are coming out of these different enterprises, but we're kind of open to adjusting this number also. And there may be a normalized or stepwise function for saying this is a startup and this is Google, right? And then the second one is we did engineer the engineered parameter, and we did that as a stepped range. So 110 million engineered parameters. It's actually not as big as you would think it is. It sounds big if you're not in the field, but the newest transformers have billions of parameters, and even some of the more complex CNNs will have in the upper hundreds of millions and up to the billions depending on the different architectures. So anyway, so just kind of walking through that the parameters and how you would actually work through them. Another transformer type example, language model type example, natural language processing is GPT-3. Again, we adjusted this to where if you'll look, GPT-3, for instance, has 31 authors. And the engineered parameter, this is 1.75 billion parameters. And this is just in their accessible model that they provided. They said they have bigger ones. And there's actually a few bigger transformers out there. But again, you can see we're at a higher risk value here. So now, we talked about how to walk through it. We talked about what the parameters look like and why we might choose them. Now, I think the important part is kind of put it all together and kind of look in here and say, how would we evaluate ourselves? Like, you look here at the bottom, we have my model. And you can see that our adversarial risk N is 0. Well, why is it 0? Well, is it publicly available? No, I don't provide API access to my model. I don't have risk today. You could have internal attackers and all that kind of stuff, but that's a whole different level of problem. In the cyber domain, they kind of break that down into different profiles. Who are your external attackers? Who are your internal attackers? Who's coming at you from these different places? We restrict ourselves to publicly available and accessible models. But I wanted to illustrate the fact that if you don't provide people access, or you provide them very, very limited access, then your adversarial risk, they would have to attack you a perfect job on the first shot or the second shot if you only provide them a few models. That's why the biggest things to get out of it is controlling access to your model, and controlling access to the model weights is pretty important in terms of protecting your intellectual property and protecting yourself against some of these folks. So, and then we have some assumptions here, just how did we actually normalize some of these particular values so that the table just doesn't look crazy. Because, if you start putting in 110 million here and 0.7 there, it gets to be almost nonsensical. And also the other part that's kind of interesting is the very growth of the models. If you looked at how many millions of parameters were in models just 7, 8 years ago versus today, I mean, their magnitude is different, right? And so this equation, this probabilistic framework, does have to adapt to the times. And as these models continue to grow, as the adversarial risk profile continues to change, I do believe that this framework would have to be adapted in terms of the new risks that you would find in particular places. So, just walking through the last few slides here, the correlation between related variables in this construct. Within figure 2, I learned how they correlate to adversarial risk. The most correlated variable in predicting adversarial risk is the learning ratio. So how aggressive are you in learning information in your particular model? The fraction of learning ratio is highly correlated to the number of parameters. Totally makes sense, because the number of parameters learned is going to be based on how aggressive the learning ratio is. So you're going to have a high correlation there. The fraction of high input supervisory guidance is related to the fraction published. So, of course, if you're going to go publish it, at least you would hope that some of these models are being checked, some of them are being evaluated, and you're getting some information back out of them. And finally, the fraction of completed queries is also correlated to the fraction published. So a lot of these models that are getting published out there are getting hit really hard. And I like, I'm a little pessimistic in this regard, but some of that's publicity wise, right? OpenAI is not releasing GPT-3 out of the good grace of their own heart. They're releasing it to show that they have this kind of mind-bending ability to build giant transformers that are really good at some downs. And it does not surprise me that those factors are actually very correlated. So finally, in conclusion, the biggest challenge in finding novel utility for this framework kind of shares much in common with Drake's original notion. How are we quantifying these factors? Which factors show strong correlations? And we touched on this earlier. How do factors change with time, particularly both if the builders and attackers modify their behavior? So let's say we take all this into account, we start accounting for all these different risks, and we're making sure that we're paying attention. The attackers are going to adapt. The cybersecurity domain is the perfect example. You can do everything in your power to do the right thing, and you can still fail. There's not much that says we can ever be perfectly protected from an adversarial attacker. Even if you don't have folks query it, there's still other avenues for them to get to it. We talked about insider attacks, and we talked about other ways that folks could actually go in and poison the data. So somebody doesn't even have to go and touch your model. They could just poison the data set they know you're going to get, and now you have a vulnerability built into your model. Last is, what are the appropriate units to assess machine learning risks, either as the number of or severity of adversarial attacks? So, is it a risk factor, or is it the number of attacks? I think without having a quantified number of attacks, I prefer the adversarial risk factor strictly from the fact that we could identify that as an engineered parameter that we've estimated, and then walk back to the attacks we actually observed. So that's it for my presentation. I really appreciate y'all's time, and I'm just going to open up the questions if anybody has any questions.